Good morning. This year, Maud and I decided to work on a subject entitled Planetary Clock. Our goal was to devise a clock which would be able to work using only the rotation of the Earth. We wanted this clock to be able to work on different planets and to have a precision of under a minute. The first part of our work was to study systems which are able to detect the rotation of the Earth. We especially focused on three of them: Foucault's pendulum, Foucault's gyroscope, and the optical gyroscope. Both gyroscopes, though extremely complex, don't show any sort of periodical patterns. That is why they are fundamentally improper to build a clock. That is why we decided to focus solely on Foucault's pendulum, as it actually shows periodical patterns directly linked to the rotation of the Earth. So, what is a Foucault's pendulum and how does it work? It is made up of a heavy sphere attached to a long string or linked to a fixed structure. Given its scale and the way it is built, the pendulum doesn't feel the Earth's rotation. In other words, the axis of oscillation of the pendulum doesn't rotate, even though the Earth is rotating. So, for an observer looking at the pendulum, it may appear that the axis of oscillation of the pendulum is rotating, but in reality it's the observer that is rotating around its fixed axis of oscillation. Now let's look at the theory behind the Foucault's pendulum. To do so, we'll use Newton's second law on the pendulum in the terrestrial reference frame, which isn't Galilean. The forces that are applied on the pendulum are its weight, the tension of the string, friction force, and, more importantly, the Coriolis force, which is the direct result of the non-Galilean aspect of the terrestrial reference frame. This force is an axial force, and it will push, in a way, the pendulum on the sides. That is why an observer will see a rotating, oscillating plane of the pendulum. One can solve this equation in the ideal case, that is to say, without friction force, and we obtain the following solution, which, even though it appears to be quite complicated, it clearly shows the periodical patterns presented by the Foucault's pendulum. And this is this periodical behavior that we will use to build a clock.
So now let's talk about our experimental setup. Here you have the schemes of our setup. You can see that we used a steel sphere, so that it's a heavy sphere that is attached to a piano string thanks to a screw. The piano string is in a hole and pressed under a bolt and a washer. The screw and the hole are totally symmetric, and you can see on the right that we used a steel plate so that the structure doesn't move when the pendulum is oscillating. So now, if you want to create your own Foucault's pendulum, you have to respect four important parameters. First, your setup has to be totally symmetric. Your fixating point between the sphere and the string and the structure has to be totally symmetric, or you are going to create some virtual forces that could disturb the oscillations of your pendulum. Then, the sphere that you are using has to be really dense, so as small as possible and as heavy as possible, because we would like to neglect the friction force in the theory. Then the mass of the string has to be as small as possible to neglect it in the theory. And the string has to be a monofiber string so that your pendulum is totally symmetric. Here you can see a theoretical simulation that we did thanks to the MATLAB hardware. So you can see that with or without friction force, our pendulum is going to turn around its fixating point along the time. You can also see that the angle of the oscillating plane of our pendulum is going to change linearly along the time. Here you can see the way that we followed the evolution of the angle of the oscillating plane of our pendulum along the time. Here is the oscillating plan of our pendulum at the initial time. We can thus clearly see the evolution of the angle of the oscillating plan of our pendulum along the time. Here you can see the oscillating plan at the initial time, here after 1 hour and a half, and here after 3 hours and a half of oscillation. We then just reported the several points that we get thanks to the tracker software that I showed you before, to get the several angles at the initial time after 1 hour and a half and after 3 hours and a half. We then just did a small calculation to show that our angles evolved in the same way as time. So we proved that our pendulum is turning around its fixating point just as time is evolving. Since our angles are evolving proportionally to the time, we can thus conclude that our pendulum can indicate the time thanks to the angle of its oscillating plan. So now if you want to adapt your pendulum on another planet, you will just have to measure the new value of J on this new planet thanks to the measurement of the weight of a specific mass with a string, so that you will get the proportionality factor between the oscillating period of this new planet and the oscillating period of the Earth, so that you will get the evolution of time on this new planet. So thank you for your time, and thanks to the several supervisors that help us a lot during this adventure. And let's just finish with some pictures of our structure and our Foucault pendulum.